Hello and welcome to my reassessment presentation of campus programming of data analytics. My name is Rajveer Dhariwal and my student ID ST20313299. The title of this project is Beziling Multi-Site Air Quality Analytics and Application Development. In this project, we worked with a real-world air pollution dataset collected for multiple monitoring stations across Beijing to understand the relationship between environmental and meteorological factors and predict PM2.5 pollution level using machine learning. My work covers the entire data pipeline from data algorithm and cleaning throughout expertise, data analytics, and model building to the development of an interactive streamed web applications that allow users to explore the data and predictions. This reassessment also gave me an opportunity to reflect on my previous submission, where I made a critical mistake by using the wrong data set. I will use the feedback continuously, improve every stages of my work, and I'll explain how as we go through the slides. Data handling. Starting with the data handling, this was the foundational step of this project. The original dataset consists of 12 separate CVS files, each representing and monitoring stations basing. The stations continuously record air quality indicators and meteorological conditions, giving us a massive dataset covering over 4 years of hourly observation. To make the process efficient and repeatable, I created a Python dictionary that mapped each station's name to its file path. That allow me to log through the dictionary and load of 12 file programmable using Panda Read CSV. To maintain the visibility of the data sources, I added a new column named site name to each dataset, identifying which moderating station the data belonged to. After all the dataset were prepared, I Pandas concept to merge the vertically and single data frame. Name it. Combine data I include ignore index true to reset the index and ensure the new data frame was clean and usable. I also performed some basic inspections using head shapes, data types, issues, and null to verify the merge of successful and to understand the structure quality of the data. Finally, I exported to the merged dataset a new CSV file which allowed to issue in future steps within repeating the import and merge logic. Challenge in data handling. Although the merge process was stimulating, there was a number of challenges I faced during the data handling. One of the highest issues was the presence of missing value in several key populating columns, especially the column CO and O2 and O3, had thousands of missing entire this variable important input for the machine's learning module, so handling their missing values effectively was installed. The VD column which representing wine decorations was another challenge. The column is categorically and contains string value NWSC. Its machine learning algorithms require numerical input. I had to design a strategy to import missing value and then encode them. Another considerations were the mixed data types. The data contains integers like month, hour, float like PM215 temperatures, and strings like station's name, ensuring that all columns were in the correct format before modeling was crucial. Lastly, the dataset large with 4,20,000 rows and 19 columns. The mean that an efficient operations could slow down the processing or even cause memory issue. Therefore, I had to mindful of performance when merging and data, transforming the data. And the exploratory data analytics (EDA), with a clean and merged dataset in place, I moved to on the exploratory data analytics of EDA, an essential step to extract insight and inform model design. I started with enumerated analytics, exploring the distributions of individual variables like PM2 1.5 and PM10 CO and SO2 using histograms and kernel density estimations plots. Most pollutants showed right scavenger distributions, indicating the while most values are low. There are occasional pollution spike that aligns with typical real-world behavior in the urban air quality. Next, I performed BFT and multivariable analysis used to scalar plots of correlations, attempt to examine relationship between feature. One key observations was the strong correlation between PM2 1.5 and PM10 with a confidence of about 0.88. This confirmed that these pollutants often rise and fall together. I also found meaningful positive relationship between CO2 and NO2, suggesting they may originate for similar sources like traffic or industrial emissions. Additionally, I used to box plot for examining of PM2 1.5 levels are across different and monitoring stations. This helped identify patterns over time and highlighted locations with consistently high population levels. These insights were useful when selecting feature for the prediction module and the data pre-processing. After understanding the data of is a pattern, it proceeded with data pre-processing to prepare the dataset of machine learning. First, I address the missing value for numerical columns like PM2 1.5, CO2, CO, and NO2. I used median imputation, which is more reversed than the mean when outlier are represented for the categorical columns WD y directions. I used mode imputations, replacing missing value with the most common and bind direction. This was a practical approach given the nature of the data. I also performed one-hot encoding on categorical columns such as station and site name, converting them into binary columns. The cloud be used to the model. Our numerical feature was standardized using standard scalar for skills learning. The steps ensure the features like temperatures and winds and populations levels are of the same scale, preventing modules like XHG boost from being based towards feature with large numerical range. Final, I performed feature engineering by extracting new insight for exiting time-based feature, such as grouping by year of hour to reveal temporal patterns and exist in the future trend modeling. With the dataset cleaning, encoding, and scaled, I was ready to build and evaluate the machine's learning module. Model training XGBoots. With the data fully pre-processed, I move on the building to machines learning module. The goal was is predict BM2 1.5 levels, which are now the post-series health risks at high concentrations. After evaluating several model options, I selected XGBoost researchers due to the proven effectiveness on structured tabular data, ability to handle missing value, and strong performance on non-inliners relationships. For input features, I used key environmental and meteorological variables including PM10, NO2, CO, SO2, temp, WAMP, rain, and WSPM, along with station and site name, including as one hot vectors. I divided the dataset using 80-20 trained stat supply to ensure the model was trained on a large sample while preserving unseen data performance in evaluations. The intentional model achieved promised results. Mean absolute error MAI 13.91, root mean squared error MSE 22.22, R to score 0.9229. This indicates that modules explains over 92% of the variance PM2.5 levels, which is strong baseline for environmental predictions. Hyperparameter tuning. While the baseline models performed well, I wanted to improve its accuracy and generalizations by using hyperparameter tuning. I implemented grid search CV, which performs to executive search over specified parameter value combined with fivefold cross validations to ensure the result were robust across different data splits. The parameter I in turn included the number of trees in the imageable, max depth, the max depths of the each tree, learning rate, the step size of each iterations, subsamples, the fractions of row and use to the training each tree. After optimizations, the model's performance improved as follow optimizers ME 13.32, RMSE 21.40, R2 score 0.9284. These results show only lower predictions error but also increase explained variation, confirming that the tuned models generalized better and was more reliable estimating PM2 1.5 levels under various conditions. Streamlit application. After building and validations the model, I developed an interactive Streamlit applications to present data and predictions in a user-friendly format. And the app is structured across the three T's: maintain clarity and modularity. And I choose Timid. It is simplify speed and ability to deploy interactive Python-based web apps without requiring front-end coding. The app offers seamless walkthrough of the project's logic, making it is accessible for the both technical and non-technical audience. Challenge and limitations. Like a real-world project, one also presented several challenges and limitations, both technical and conceptual. The most immediate challenge was data quality, particularly the missing value in the key pollutant columns such as CO, NO2, and O3. While limitations helped, there's always a risk of introducing noise, noise or basis. Another limitations involved extremely predictions error. Although the models say average performance was strong, occasionally made large error. With the maximum error exceeding 600, this may be accused by authority of sudden population spikes that the module could not generalize well. I also encountered concentrate with Streamlity, which the fast and intuitive like advanced UI customizing unless integrated with JavaScript or external styling. Most importantly, my previous submission failed use the correct dataset, which means the entire workflow was mislining as assessment brief. There was key issue highlighted the feedback and become my primary focus during the reassessment to correct and improve. Recommendations and future work. Based on my finding and experience, I several recommendations for future work that could enhance the performance, usability, and impact of this project. First, I recommended incorporations the TCD modeling approaches like LSTM, long short-term memory networks, or Facebook perhaps, which is the better suited temporary predictions and could capture early or seasonally trend in levels more effectively. Second, I would consider building AQA qualification models PM2 values into air quality categories like good, moderate, and unhealthy would the predictions actionables for end user. Versions control. Version control played an essential role throughout the project, helping organize my code, track the changes, and manage the variations development stages effectively. Reflection on previous submissions. This submissions reassessment was a valuable opportunity for me to reflect and correct the mistake in my intentional submission. So most critical feedback I received, I had used the wrong dataset, which means the work did not align with assessment brief and was therefore invalid. So thank you for listening me and listening my presentations. Thank you. How I have grown. Beyond technical improvement, this reassessment has helped me grow significantly as a student and data analyst. First, I will become much more attentive to instructions and assessment criteria. I will learn to triple check that I am using the correct files, format and output before I processed. Secondly, the process is improved end-to-end understanding of the data workflow from raw CSV files to deployed application. I now feel the confident managing large dataset, performing exploratory analytics, engineering features, and building interpretable modules. I will also developed strong skill in tools interactions, bringing together Python, Streamlit, Git, and libraries like Skittles, Learn, and XGBoost into the Oriental's functional system. Lately, I will develop a growth mindset rather than seeing feedback and criticisms. I now see Vihai's guide to full self-improvement. This assessment challenges must be raised above a park mistake and produce something I can truly be proud of. Reference to conclude, here the references the supporting my work.